Okay, so going back to this here. All right. So as I was saying, right, this is the delta E here. I'm going to replace it with HC lambda here, and that would be equal to minus RH times 1 over N2 squared minus 1 over N1 squared, right? And then what I'm going to do is I'm going to bring the HC to this side, from the left side to the right side. The only way you can do that is you divide both sides by HC. So therefore, when you divide both sides by HC, you're going to end up with 1 over lambda is equal to minus RH over HC times 1 over N 2 squared minus 1 over N1 squared, right? Now, you should recognize that this here is basically a collection of constants, right? RH is a constant, which is equal to this. H is Planck's constant, and C is the speed of light. So what I'm going to do is put the numbers here in this equation here, and you're going to see what the result is. So 1 over lambda will be equal to minus RH, which is 2.18 times 10 to the minus 18 joules, divided by H, which is 6.63 times 10 to the minus 34 joules second, times the speed of light, which is 3.00 times 10 to the 8 meters per second, times 1 over N2 squared minus 1 over N1 squared, right? And then we're going to do the calculation. So 2.18 times 10 to the minus 18 divided by 6.63 times 10 to the minus 34 times 3 times 10 to the 8. And according to my calculation, we round it off to 3 sig figs. All of this here would be equal to minus 1.10 times 10 to the 7. And the units would be meters to the minus 1 because the joules will cancel out here and here. Seconds cancel out here and here. So here we have meters below the division sign right there. So that is the result of all of this here. And then I'm going to continue to write down the rest, which is 1 over N2 squared minus 1 over N1 squared. And that is the result. So 1 over lambda would be equal to this equation right here. Now, here's the kind of weird thing. In a lot of chemistry textbooks, and even online, you'll see this being expressed or stated as being the Rydberg equation, right? In other textbooks, they will say this is the Rydberg equation, all right? And I even checked up to day before yesterday, just to be sure, right? If you look at different chemistry sources, they state that either this or this is the Rydberg equation, all right? When I was in college, this is what I learned. But over the years, they start introducing this apparently as another way of expressing the Rydberg equation, all right? So I just thought I should make mention of that so that you're not confused, when you read your textbook, whatever, all right? And both equations are useful, right? Because this equation can be used to determine the change in energy when the electron transitions from one orbit to another. This equation can be used to determine the wavelength, right? All you have to do is plug the numbers in. That will be equal to 1 over lambda. And to get the actual value of lambda, you put 1 over that value, and that's how you get the wavelength, all right? So that's basically what I forgot to mention last time, all right? Okay, any questions about this? Any questions? Okay, so let us, I think the last time we were here, we were doing, let me see here. We were doing some problems. I can, let me go here. Assignment number 7. I think we stopped in the middle of one of them. Gosh. Did we get as far as Number 4. 4A, 4B.
I think we got as far as 4.
4B. Okay, so 4A, as for the frequencies, oh, I remember now. So I focused on using this number here. And I told you guys that you guys have to do the same thing using this wavelength, all right? So A was calculating the frequency, B was calculating the energy, and now C is asking for you to calculate the molar photons of light with each. No, hold on. I think this is a typo. Okay, this is a typo. So please make a note of this. What C is asking for is calculate the energy of a mole of photons with light with each of these wavelengths. That's what the question is asking for, all right? Now, in order for us to answer that question, I need you to remind me of what the energy that was calculated in the A part. What was the energy that we calculated in the A part?
For the 4.7 nanometer one, 4.91
4.91
times 10 to the negative 19.
10 to the minus 19 joules? Okay. So that would be the energy of a photon. So that's the energy per photon, right? What the question is asking for is the amount of energy per molar photon. So that means that we'd have to multiply by Avogadro's number, 6.02 times 10 to the 23 photons per mole. And that's it. Let's see what this gives. 4.91 times 10 to the minus 19 multiplied by 6.02 times 10 to the 23. And according to my calculations, this rounds off to 2.96 times 10 to the 5. And the units here would be joules per molar photons. And that's how that is done. All right? Okay, any questions about this one? Any questions? Any questions? Okay, let's clear this and scroll down. Okay, okay, so this question is asking for you to calculate the longest and shortest wavelength of light emitted by electrons in the hydrogen atom that begin in n equals 6 and then fall to states with smaller values of n. Now, I just showed you this equation. Let me squeeze it over here. That delta E, which is the energy change in the transition, is equal to hc over lambda. And one important observation we can make based on this equation is that there's an inverse relationship between the change in energy and the wavelength associated with that change, right? In other words, the longer the wavelength, the smaller would be the energy gap between the two orbits of the transition, and vice versa, right? So what this question is saying is that you need to find the longest and shortest wavelength. The longest wavelength would correspond to the smallest energy gap between the orbits of the transition, and the shortest wavelength will be corresponding to the longest or the largest energy gap of the orbits involved in the transition, right? And the question continued to say that you're starting from n equals 6, and then the electron will fall to states with smaller values of n. So something like this, I like to use a diagram to represent what's going on here. So what I'm going to draw here are the different orbits. Okay, already making a mistake. Okay, so this is n equals 6, this is n equal 5, and then this is n equal 4, and then this is n equal 3, and then go no further. This is n equal 2, and this last one, which is closest to the nucleus, is n equal 1. You'll notice how I space them out, because what happens is that as you go from one orbit to the next, higher and higher, the spacing decreases, all right, between the orbits in terms of their energy, right? So let's deal with calculating the longest wavelength. The longest wavelength, as I said before, based on this expression, would correspond to the shortest energy gap when the electrons are leaving from n equals 6. That means basically the electron is leaving from n equals 6 to n equals 5. All right, that's the shortest or the smallest energy gap, right? So basically, the equation that we're going to use is this form of the Rydberg equation. Delta E is equal to minus RH times 1 over n2 squared minus 1 over n1 squared. So minus RH is equal to minus 2.18 times 10 to the 18 joules multiplied by 1 over n2 squared. So we're going from this, which is the final, I'm sorry, this, which is the initial, n equals 6, to this, which is the final. So therefore, 5 squared, that's the final, minus 1 over 6 squared, which is the initial. And that's, oh, shoot, okay. I'm going about it a longer route. Forgive me, I have to erase all this here. I apologize. I should have been more careful because of what the question says. The question is asking for the wavelengths, right? Not the energy gap, right? So that was my mistake. So the equation you're going to use is 1 over lambda is equal to 1.10 times 10 to the 7 meters to the minus 1 times 1 over 5 squared minus 1 over 6 squared. All right? So I would use this form here because the question is asking for the wavelength, right? As opposed to what I showed you before. And let me also mention too, I should have mentioned this earlier. Again, in some textbooks where they use this equation for the Rydberg equation, this is called the Rydberg constant, RH, right? As opposed to the other RH, which I showed you before, all right? So again, that's basically how things are in terms of expressing the Rydberg equation in different ways based on different chemistry sources. Anyway, so all we have to do now is the math. We plug the numbers in, and we're going to end up with, okay, I'm going to work out what's within the parentheses first. And then I'm going to multiply by 1.10 times 10 to the 7. And the answer I got here is 1.34 times 10 to the 5. And the units here will be meters to the minus 1. So therefore, lambda itself will be equal to 1 over that, 1 over 1.34 times 10 to the 5 meters to the minus 1. Let's see what that gives. So according to my calculation, this gives 7.44 times 10 to the minus 6. All right, so this would be the longer or the longest wavelength. All right, and the units, by the way, will be meters. And that's how that is done. All right? Any question about that? Any questions? Any questions out there in Zoom? Okay, now to get the shortest wavelength, basically that would correspond to the delta E being the largest possible, right? Which means that in this case, you're talking about going from n equals 6 to n equal 1, right? Delta E for that would be the largest energy gap, which means that the smallest wavelength would be based on the initial n value would be 6 and the final n value would be 1. So basically, all I have to do is change this here from 5 squared to 1 squared. And then we do the same calculation. So in this case, it's 1 minus, okay, and then I multiply that by 1.10 times 10 to the 7. And according to my calculation, let me just erase this here. Oh, I keep screwing up today. I don't know why. But anyway, the value you're going to get here is 1.07 times 10 to the 7 meters to the minus 1. Okay, so here's where I screwed up again. I forgot to put a negative sign here. Remember, the negative sign should be there, right? Which means that the negative sign should be here. And that's true for the first one as well. This should be negative. This should be negative. However, right? And this is very important. Whenever you're using this equation and you get a negative wavelength, you need to understand that there's no such thing as a negative wavelength, right? What the negative sign indicates is that radiation is emitted, all right? So basically, the longest wavelength actually would be the absolute value, 7.44 times 10 to the minus 6 in this case. And in this case, it would be 1 over lambda in this case would be 1 over 1.07 times 10 to the 7 meters to the minus 1. And let me see what that gives. So this gives 9.35 times 10 to the minus 8. 9.35 times 10 to the minus 8. So even if you get a negative answer, right, in terms of the wavelength itself, understand that that negative sign only indicates that radiation is emitted as the electron falls from higher energy orbits to lower energy orbits, all right? So that's basically how that is done. Okay, any questions about this? Any questions? Yes, ma'am.
So like on the assignment and on the test, do you want us to write it as the absolute value?
Yes.
Okay.
If you get a negative lambda value, right?
Write it as a positive.
Write it as a positive because there's no such thing as a negative value for the wavelength. The negative sign only indicates that radiation is emitted. Okay, any other questions? Any other questions? Alrighty, so let me clear this and scroll down. Okay, so this question says calculate the change in energy when an electron transitions from n equals 3 to n equals 2 in a hydrogen atom, and what does the sign signify? So in this case, because the question says change in energy, this is the formula I would use, delta E. That would be equal to minus RH times 1 over N2 squared minus 1 over N1 squared. And then we put the numbers in. RH is minus 2.18 times 10 to the minus 18 joules times 1 over the final N value is going from 3 to 2, so that would be 2 squared, right? Minus the initial N value, which is 3, so that would be 3 squared. And then that's it. We do the number crunching. And I got, and please correct me if I'm wrong, but this is what I got, minus 3.03 times 10 to the minus 19 joules, all right? And the question says, what does the sign of the energy signify? In other words, what does the negative sign signify? It signifies what?
That a photon with that energy has been released.
Exactly. Energy is released as a photon goes from 3 to 2, and that's it. Okay, any questions about this one? Any questions? Okay, let me clear this and scroll down. Okay, so this question is a bit different from the others. You're still using the Rydberg equation. It says, using that formula, calculate the energy level when an electron in a hydrogen atom transitions into n equal 2 and emits a photon of 410.1 nanometers, right? So some very important points that you have to pay attention to in this question. It's asking for the initial energy level. So basically, this is asking for N1, right? When an electron in a hydrogen atom transitions into n equal 2, so that would be N2, right? And emits a photon, very important, emits a photon at 410.1 nanometers, right? So the equation I would use would be 1 over lambda is equal to RH times 1 over N2 squared. Oh, don't forget the negative sign. Minus 1 over N1 squared, right? So this is the equation we're going to use, right? And what we need to find is N2, which is right here, right? So first thing I'm going to do is take care of the left side of the equation. 1 over lambda. Now, lambda is equal to 410.1 nanometers, which we have to convert to meters. So nano means 10 to the minus 9. So I'm going to put 10 to the minus 9 meters above and 1 nanometer below. Now, because the question says that photon is emitted, that means that we have to put a negative sign here, right? Because remember from the previous example where we had a negative wavelength, that means that the photon is emitted. We have to do the same thing here. We have to put a negative sign here. And then I'm going to set that to be equal to minus 1.10 times 10 to the 7 meters to the minus 1 over 1 over N2 squared, right? Which is what we're trying to find. I'm sorry. We're trying to find N1 squared. So N2 is 2, actually. So let me change this here. This is going to be 2 squared. 2 squared minus 1 over N1 squared. So N1 squared is what we're trying to find, all right? So now we have to just do some algebra. How are we going to deal with this? I would divide both sides by 1.10 times 10 to the 7 meters to the minus 1. So when I do that, I'm going to end up, well, firstly, these signs will cancel out each other. Then I'm going to do 1 over 410.1 nanometers converted to meters, 10 to the minus 9 meters over 1 nanometer. And then I'm going to multiply by 1.10 times 10 to the 7 meters to the minus 1. And that would be equal to 1 over 2 squared minus 1 over N1 squared. So I'm going to work out the left side. 410.1 times 10 to the minus 9 times 1.10 times 10 to the 7. And then I'm going to do 1 over that. So what I got on this side here is 0.22. Actually, let me see here. 366, so 0.222. All right? And that would be equal to 1 over 4, which is the same thing as 0.25, minus 1 over N1 squared, right? And then, let me erase the top part because I'm going to need some space. So I'm going to just continue above. So basically, as a result of that, we can say that 1 over N1 squared is equal to 0.25 minus 0.222. And let's see what that is equal to. So I got 0.0283. All right. And then to get N1 squared, that will be equal to 1 over 0.0283. So let me see what that gives. That gives 35. So therefore, N1 would be equal to the square root of 35. Actually, let me make this 35.3. This should be 35.3, 35.3. So to find the square root of 35.3, I got 5.9. Now, because N1 should be an integer, we can simply approximate this to 6. And that's how we solve that problem. All right? Any questions about this one?
Yeah, so when you're subtracting, do you want us to use the sig fig
Oh,
stand?
good question. So the thing about it is that 25 here comes from 1 over 2 squared, right? 2 is an exact number.
Okay.
So this, as a result, would be exact as well. 1 over 2, 1 over 4 squared would be exact.
Okay.
This has 3 decimal places.
Mhm.
So basically, because this is exact and that has 3 decimal places, this determines the extent to which you round this off, right? Actually, this should be 0.028. Thank you for pointing that out. So let me, the answer should still be the same. Let me see here. So this should be 0.028. Let me see what that gives. 1 divided by 0.028. So that gives 36, 35.7, not much of a change, right? 35.7. So when I find the square root of that, I'm going to get 5.97, which again approximates to 6. So it doesn't change the answer. But that's a good question to ask. You have to keep in mind that the n values are exact values, right? They're not obtained by measurements. It's basically by definition. All right? Okay. Any other questions about this? Any other questions? Any other questions? All right. Let me clear this and scroll down. Okay. Number 8. Let me hear your ideas about this one. How would you tackle this one? I guess the important question is, which formula do you use? Because remember, there are 2 forms of the Rydberg equation. So which one of the 2 would you use? Would you use the one with delta E, or would you use the one with 1 over lambda?
1 over lambda.
1 over lambda, right. So 1 over lambda will be equal to minus RH times 1 over n1 squared, I'm sorry, n2 squared minus 1 over n1 squared. All right? Okay, so what are the numbers we're going to put in? Minus RH is, or RH is what?
1.1 times
1.10 times 10 to the 7, m to the minus 1, multiplied by 1 over what?
1 over 3 squared.
3 squared minus
1 over 1 squared.
1 squared, exactly. That's it. So let's see what this gives. Okay, and then I multiply that by 1.10 times 10 to the 7, and put a negative sign. Oh, so the negative sign become positive because this part here comes out to be a negative number. So the final answer is going to, well, not the final answer, 1 over lambda is going to be minus, it's going to be 9.78 times 10 to the 6 meters to the minus 1, which means that lambda is equal to 1 over that. So let's see here. So according to my calculation, that works out to be equal to 1.02 times 10 to the 7 meters. And that's how that is done. All right? Any questions about this one? Any questions? Okay, moving along. There it is. Let's see if there's any more we can do after that. Okay, I don't think we can do this quite yet. So let me go back to the PowerPoint. And we're going to talk about the de Broglie equation. So that means we're going to start from here. Okay, so I think I mentioned earlier that when it comes to waves, or I should say specifically when it comes to electromagnetic radiation, it turns out that they behave in 2 ways, which seems kind of counterintuitive. In one sense, electromagnetic radiation behaves as a waveform. In another sense, it behaves as a stream of particles known as photons, right? And in your textbook, I think they have this term, write it up here. I'm just going to squeeze it up here. Wave particle duality, right? In other words, when it comes to electromagnetic radiation, they behave in some aspects like a waveform and in other aspects as a particle or particles moving, right? So this guy by the name of de Broglie, he looked at this and he said, well, if that is true for electromagnetic radiation, then what about any ordinary object that is moving? Does it have a waveform associated with it? So he did some theoretical work, and I won't go through all the steps that he went through. He came up with this equation right here, right? Which basically describes a wavelength associated with any moving object. It doesn't matter what it is, right? So let me just define the terms here in this equation. Lambda is the wavelength associated with a moving particle. Wavelength. Which in this case would be in meters. H would be Planck's constant. Which in this case would be joules second. M is the mass expressed in kilograms. And V, is the velocity or speed, which is expressed in meters per second, right? So basically what de Broglie is saying, and let me apologize if there's anybody who speaks, I think he was from France. I may have massacred his name, so please forgive me for doing that. But what he was saying was that any moving object, anything that moves has a wavelength that's associated with it that can be calculated using that formula, all right? And this is one of those examples in science where somebody comes up with an idea or make a discovery, basically for the sake of trying to find out what's going on or what the nature of the particular issue is. And as a result of his results, then other people take the ball and start running with it and developed the world's most powerful microscope, which is known as the electron microscope, right? That operation, the operation of the electron microscope, is based on the equation that de Broglie developed, all right? Okay, so that's de Broglie's equation. Now, since we have done that, we now should be able to do the next question in the handout, in the assignment. So let me go to it right here, and let me clear this page. Okay, so number 9A says, what is the velocity of a neutron? And it gives you the mass of the neutron, which exhibits a wavelength of 580 nanometers, right? So remember now the equation I just gave you was this, right? Lambda is equal to h over mv. What the question is asking for is v, right? So we can rearrange this to get v is equal to h over m lambda. And then we put the numbers in. So h is 6.63 times 10 to the minus 34 joules second divided by m, which is the mass. Now remember I said that the mass must be in kilograms, right? And they gave us the mass in grams. So 1.67 times 10 to the minus 24 grams, we convert to kilograms. So to do that, we're going to put 1 kilogram above as the numerator, 1,000 grams below as the denominator, and then we multiply by the wavelength, which is 580 nanometers. But remember we said that the wavelength in this equation must be expressed in meters. So again, we have to do another conversion where we put 1 nanometer down here and 10 to the minus 9 meters above. And that's it. We do the crunching of the numbers. I'm going to start with the denominator below. Divide by 1,000. And then multiply by 580. And then times 10 to the minus 9. And then 1 over that. And then multiply by 6.63 times 10 to the minus 34. And the answer I got when rounded off to 3 sig figs is going to be 0.6, actually 2 sig figs because of the 580 here. So that would be 0.68. 0.68, and the units would be meters per second, all right? Now, you might be wondering, how do I know that the units here would be meters per second? Well, apart from the fact that that's a unit of velocity or speed, this joule unit here, I think I mentioned it in the previous chapter, that the joule unit is the same thing as kilograms meter squared over second squared, right? So if I were to replace J here with kilograms meter squared over second squared times S here, then you're going to see how the units cancel out, where the kilograms will cancel out here and here, the grams will cancel out here and here, nanometers will cancel out here and here, and this meter here will cancel out one of the meters here. So your final units will be meters per second. All right? Okay, any questions about this? Any questions? Any questions? Okay, so if you understand how I did number 9A, then you should be able to do 9B. So I'm going to leave that for you to do on your own. In the case of 9B, it's the same equation, but this time they're asking for the wavelength, right? So basically, you'll be using this equation directly. All you have to do is put the numbers in, make sure that the units are correct, and that's it. You're going to get your answer, all right? So you can do that on your own. If you have any problems, please come and see me or call me or whatever, and I'm more than willing to help you out, all right? Okay, so let me clear this here, and let me scroll down further. Okay, so we won't be able to do that right now, so let me go back to the PowerPoint. All right, so what's the next topic? Okay, so here's where things get really interesting, and I can totally understand if some of this you might not be able to appreciate immediately. So let's talk about this principle here known as the Heisenberg uncertainty principle. And this, in part, explains why the Bohr model, even though it works well for hydrogen, it is now considered not a true representation of how the electrons are arranged in the atom. So this guy here by the name of Heisenberg, he came up with a law, a principle, which says that we cannot know exactly where a tiny particle like an electron is and exactly how it's moving. In other words, another way I've seen it expressed is that it's impossible to know simultaneously the location of a particle like an electron and its speed or momentum, all right? And the reason why is because the act of determining where the electron is actually interferes with the particle, and therefore you won't know where it is based on the interference. And just to demonstrate what we're talking about here. So let's say, this is purely, hypothetical or theoretical. Let's say you have a special microscope that you can see an electron, all right? In order for you to see an electron, however, you need reflection of light of the electron so that you can see it in the microscope, right? That means that a photon of radiation would have to hit the electron, and then that bounces to the microscope so you can see it. Problem is that when the photon hit the electron will move, right? So at that instant, where you think you have seen the particular electron, the electron is not there at that instant. So that's basically what the uncertainty principle is saying. Now, the consequence of that is that the Bohr model that we were just discussing, again, as I said before, it works well under certain circumstances, but we now know based on this principle that the Bohr model cannot be true, because what the Bohr model says is that we know where the electron is. Let's say we're dealing with the hydrogen atom. We know that the electron is within a well-defined orbit. The uncertainty principle says, no, you cannot tell where the electron is, right? So therefore, that means that more theoretical work has to be done in order for us to really determine how the electrons are located or arranged in an atom. So this brings us now to the wonderful world of quantum mechanics, right? Quantum mechanics is basically an approach where instead of determining or try to determine where an electron is, we try to instead determine the probability of finding an electron within a certain region, right? And this is, I can tell you that this area of science is not 100% understood, right? Unfortunately for you guys, you don't have to delve into this particular topic too deeply, unlike when I was in grad school. I still don't have fond memories of that experience. So thankfully for you guys are just going to get the results of, the approach. This is the guy who is responsible for this field being invented and developed. And basically, the main idea behind this treatment is that we end up with an equation which is called a wave function, which is a solution to the Schrodinger equation. I'm not even going to show you what the Schrodinger equation looks like. If you're interested, you can look it up, but I'm not going to show you because you don't need to know at this level, right? So basically, if you find a solution, which is a wave function of the Schrodinger equation, that represents the state of the atom and especially the state of particular electrons in an atom, right? How do we interpret the wave function? Well, the wave function, when squared, gives the probability of finding an electron within a small volume of space around the atom. And we call this small volume of space around the atom where the probability is about 90% or greater. Okay, what's going on here? We call that an orbital, right? So let me see if I can squeeze in the definition of an orbital here. In fact, hold on. Hold on. Let me do something here first. Okay, so I'm going to give one definition of an orbital. An orbital is a region in space where the probability of finding an electron is greater than 90%. All right? So there are several definitions that you see in different textbooks, but this one I think is the most easier one to remember and understand, right? So that's basically what an orbital is, right? So the point here is that, as I said before, you cannot tell exactly where an electron is in an atom, right? According to Heisenberg. The best you can do is determine a region in space where the probability of finding an electron is greater than 90%, all right? And what you're going to find is that different types of orbitals will have different shapes, all right? So let me clear this here. So as stated here, the result of this interpretation leads to the idea of what is oftentimes referred to as an electron cloud, which is basically the same thing as an orbital, instead of trying to locate exactly where the electron is, because that is impossible, right? So basically, when it comes to the wave functions, they must have specific integral values, which are known as quantum numbers, right? Again, these numbers are arrived at as a result of calculations, and very complex, which we won't get into, right? So there are 4 types of quantum numbers that we're going to learn about. What time is it, by the way? Okay, we have time. Okay, so there are 4 quantum numbers, right, which basically would be useful for defining an atomic orbital. And it says here the wave function with a given set of these 3 quantum numbers. Actually, it's 4. We're going to deal with the first 3 first, right? So any wave function that has these, I would say, 4 quantum numbers, that is what is defining an atomic orbital, right? And these orbitals allows us to visualize a region where the probability of finding an electron is greater than 90%, all right? So the first quantum numbers we're going to talk about is what is called the principal quantum number, n, right? Now, it turns out that this n value is the same as the n value according to the Bohr model. So there's some correspondence between the Schrodinger wave function approach and the Bohr model, all right? So what that means is that n is an integer, and it is independent of the other quantum numbers that we're going to meet, right? N can only be a positive integer, starting from 1 all the way up to infinity, right? And it turns out that the size of an orbital and its energy is dependent on n, which again corresponds to what the Bohr model predicts, right? The higher the n value, the greater will be the energy of, in this case, an orbital, not an orbit, as in the case of the Bohr model. Okay, orbital with the same principal quantum number of n are said to be in the same principal shell or energy level, all right? So any orbitals that have the same value of n, we say that they're in the same shell or energy level, all right? Then we have what is known as the angular momentum quantum number, right? And it is symbolized by the letter L. Now, the thing about these numbers is that they are corresponding to the shapes of the different orbitals. And later on, we're going to see what kind of shapes we're dealing with, all right? So the values of L is dependent on the value of n, such that L would be equal to all integers from 0 to n minus 1, all right? So for example, if n is equal to 2, then based on what we just said here, L can be equal to only 0 or 1, all right? If n, let me write something down here. If n is equal to 3, then L can only be equal to 0, 1, and 2. If n is equal to 4, then L is equal to 0, 1, 2, and 3. So what would be the case when n is equal to 5? If n is equal to 5, L will be equal to what?
We work from 0 to 4.
0, 1, 2, 3, and 4, and so on and so forth, right? So those are the L values, and the L values are correlated to the shapes of the orbitals, right? So basically, all orbitals that have an L value of 0 have a particular shape, right? All orbitals with an L value of 1 will have a different shape, and so on and so forth, all right? Okay, another thing I should mention is that there's some letter designations associated with the L values. So if L is equal to 0, we say that these orbitals that have the L value of 0 are s orbitals. If L is equal to 1, then that is associated with what we call p orbitals. If L is equal to 2, then those are d orbitals. If L is equal to 3, f orbitals. And then after that, it goes alphabetically. So if L is equal to 4, then g. If L is equal to 5, then h, and so on, right? So those are the correspondings of the letters designated to the L values of the different orbitals. Okay, now let's see what's below here. Okay, so as stated earlier, I mentioned this before, each of these orbitals is a different region of space and different shape. And all I didn't mention this. So all orbitals having the same value of n and L are said to be in the same subshell, all right? So all orbitals that are in the same shell would have the same n value, but all orbitals that have the same values of n and L are said to be in the same subshell, all right? Okay, so that's the angular momentum quantum number known as, or simply the L value, all right? And then the next quantum number we're going to talk about is what is called the magnetic quantum number, which is symbolized by ML. And basically, this number here corresponds to the orientation of each orbital in space, right? And it turns out that the ML values are dependent on the L values, right? Where ML is equal to minus L and all integers to plus L. So for example, if L is equal to 2, then ML can be equal to minus 2, minus 1, 0, 1, 2. And let me just give some other examples. If L is equal to 3, then ML will be equal to plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. If L is equal to 1, then ML will be equal to plus 1, 0, minus 1, right? So what would be the case if L is equal to 0? What is ML equal to? If L is equal to 0, what is ML equal to? 0, exactly, right? So that's basically how we determine the ML values. Now, just to remind you, the ML values basically correlates to the orientation of the orbitals in three-dimensional space, right? And what we can conclude based on the ML values are the number of separate orbitals that will have the same L value. So for example, in the case of L equals 0, which would be the s orbitals, because there's only one value of ML, that means there's only one s orbital that can exist, right? In the case of L equals 2, which represents the p orbitals, they come in sets of 3s because there are 3 ml values. In the case of the d orbitals, for which, I'm sorry, d here, for which for which L is equal to 2, I'm sorry, then you have 5 ml values, which means that d orbitals, they appear in sets of 5, right? And then here, if L is equal to 3, then there are 7 ml values. That means that for f orbitals, they appear in sets of 7, all right? So that's basically what the ml value tells you. Okay, let me clear this here. Let's see what will. Okay, so this table here basically summarizes what we just discussed. Firstly, we have the principal shell number, right? N equals 1, 2, 3, all the way up to infinity. It can go all the way to infinity. In the case of N equal 1, the only possible value of L would be 0, and the only possible value of ML would be 0. So therefore, the way we designate this particular subshell, we call it 1S, right? 1 is the N value, and S is the value associated with the fact that L is equal to 0, all right? Now, in the case of the second shell, right, N is equal to 2, right? And in the case of where N is equal to 2, you can have 2 possible values of L, 0 and 1, right? If L is equal to 0, that means ML is equal to 0, just like we said over here. And the designation for this particular subshell is 2S. 2 because it's from the second shell, and S because L is equal to 0. Now, over here, we have 3 possibilities where L is equal to 1, right? So that means that in this case here, there are 3 possible p orbitals, right? So in the case of L equal 1, you can have -1, 0, +1, which would represent the individual p orbitals. And therefore, the designation here would be 2p. And there are 3 of them, right? So therefore, that's basically what happens in the second shell. And then, as you can imagine, it becomes more complex when you move to higher shells. So in the case of N equal 3, the third shell, you have these possibilities where, in this case here, L is equal to 0. In this case here, L is equal to 1. In this case here, L is equal to 2. In the case where L is equal to 0, there's only 1 ml value. In the case of L equals to 1, there are 3 ml values. And in the case of L is equal to 2, you have 5 ml values. So basically, the designation here would be 3S. Here is going to be 3p, and there are 3 of them. And here, the designations for the separate orbitals will be 3d, and there are 5 of them. And that's basically what happens. And if you understand that, then you should be able to understand what would happen next if you go to the 4th, 5th, and so on. Things become a bit more complex, but basically it follows that same pattern. Now, there's one more quantum number. Oh, before I do that, okay. So in terms of how these orbitals look, all right, the way we look at them is that we can look at it in terms of the probability of finding an electron, in the atom in terms of its distance from the nucleus. And this is what you typically see. I think this is for the 1s orbital, right? But what is normally done is that we try to find the probability of finding the electron within a volume of a sphere of radius r, and that is given right here, right? So this here basically paints a picture of what the orbital looks like. And in the case of the 1s orbital, it's going to look like a sphere, right? And again, thankfully for you guys, you don't have to do these calculations. I remember when I was in grad school, we had to do these, and I'm still recovering from that. But basically, that's what you do. You plot this versus this in terms of finding a volume of region where the possibility or probability of finding the electron is highest, and this is the result, right? Or it can be represented by this, right? And this is for the 1s orbital, all right? And you'll notice most of the probability of the electron being found is closer to the nucleus, which makes sense, right? So that's what happens in the case of the 1s orbital. In the case of the 2s orbital, it is spherical, like the 1s orbital, excepting that there's a region here called the node. When you do the similar plot as in the case of the 1s orbital, this is what it looks like. There's a maximum here, and then it goes down, and then there's a maximum here. The node is right here, or represented by where the curve hits the 0 mark. So therefore, what that indicates is that the probability of finding an electron in that region right here is 0, right? So that's basically what happens in the case of the 2s orbital, right? So in the case of the 1s orbital, there's no node, but in the case of the 2s orbital, there's one node. And what you're going to find is that in the case of the 3s orbital, there are two nodes, and it increases as you go along as far as the s orbitals are concerned. Now, the p orbitals, they have a different shape, as you can see here. These are the shapes of the p orbitals, and you'll notice that these p orbitals are at mutual right angles to each other, right? So if you remember from your math, the Cartesian three-dimensional system, axes, you have the z-axis, the y-axis, and the x-axis, right? So this p orbital is aligned along the p-axis, so we call it the px orbital. This is aligned along the y-axis, so that's the py orbital. And this is aligned along the z-axis, so that's a pz orbital. So this is what they look like separately. This is what they look like together, all right? So that's basically how the p orbitals appear. And whenever you see p orbitals appearing in any sublevel, they appear in sets of threes, all right? And then we have the d orbitals, which is even more complex. I won't even expect you to remember the shapes of these, right? But this is what they look like separately. There are 5 of them, right? And then collectively, this is what they look like, all right? So that's basically how the orbitals are shaped. And then I won't even go into the other ones like the f orbitals and g orbitals and so on. Okay, you do need to know that they exist, and you do need to remember the numbers of them, right? You just don't need to know the shapes of the D and the F and so on. You need to remember the shapes of the S and P. Those are relatively easy to remember. Okay, the final quantum number here, and I think we're going to finish this chapter. Okay, called electron spin, right? MS, right? And this one is the easiest to remember because there are only 2 numbers associated with this MS symbol. And it has to do with the fact that electrons, when they occupy an orbital, they can be spinning in one of 2 directions because the spins are quantized, right? So the quantum numbers that are associated, well, let me just say this. And again, this is something that, if you have to do physics, you're going to learn. If you have a charge that is moving or spinning, it generates a magnetic field, all right? Now, in the case of the electrons, if the electron is spinning in this direction, then the magnetic field will be pointing north to south like this, right? So we call that spin plus half. MS is equal to plus half, right? If the electron is spinning in the opposite direction, then the field will be pointing in the other direction, and the spin is defined as MS is equal to minus half. There's a rule I remember in physics where if the electron is spinning, it's called a right-hand rule. So if your fingers are pointing in the direction where the electrons are spinning, your thumb is indicating the direction of the magnetic field that is generated, right? So that's, I think they call it the right-hand rule or something like that. I don't remember exactly. It's been a while. So as I said before, there are only 2 possible values of the magnetic spin, minus half or plus half, right? And that's it, okay? And these numbers are independent of the other quantum numbers that we learned, okay? And this is just an experiment. I won't go into this, but this experiment is basically the experiment that led to the discovery of the MS values, plus half and minus half. So you may want to read up on that on your own, all right? And that's basically it for this chapter. So going back to the assignment. So in this question, it says, which of the following are possible for an electron in an atom? For the set of quantum numbers that are not possible, state what is wrong with each set. So the rules that we just learned is going to come into play here. What this question is asking, you're given some sets of quantum numbers for an electron. Which one is not possible, or which ones are not possible, all right? So let's look at the first one. The first one says n is equal to 1, L is equal to 0, ML is equal to 1, and MS is equal to plus half, right? Now, if we start from n equal 1, then the possible values of L would be what? If you remember from the rules, you may feel free to look at the rules that I covered. Exactly, right? So that is fine, right? If n is equal to 1, L will be equal to 0. Now, if L is equal to 0, what are the possible values of ML? 0. So here is where the error is. You see what I'm saying? ML cannot be equal to 1. The only possible value of ML is 0, all right? Okay, so the answer here would be that not possible because if L is equal to 0, then ML cannot be equal to 0. All right? And that's it. Okay. Any questions about this? Any questions? Any questions? Okay, let's look at B. They gave you n is equal to 9, L is equal to 7, ML is equal to -6, and MS is equal to -½ So is this possible? Why not?
N equals 9. There's no element that'll have.
You can have n equal 9. N can be any integer. N can be any integer from 1 to infinity.
Then isn't it all correct then?
Exactly. Nothing is wrong with this set here because if n is equal to 9, then it is possible for L equal to 7, right? Because if n is equal to 9, L can be equal to all integers from 8 all the way down to 0. And if L is equal to 7, then ML can be -6 because ML can be from +7 to -6 and so on. So therefore, I'm just going to write here that this is possible and leave it at that. All right? Okay. Let me clear this. Scroll down. Okay, let's look at this one. C. Is this possible or impossible?
Impossible.
Why?
Because MS can't equal 0.
Exactly. Because there are only two possible values of MS, plus or -½ So impossible because MS cannot be equal to 0. It can only be equal to plus or -½ All right? Okay, what about D? Is this possible or impossible?
Impossible.
Okay, why is it impossible? Let me write down impossible first. Impossible because,
Because n equals 1, so L can only equal 0.
right, it's impossible because if n is equal to 1, then ML cannot be equal to 1 because ML can only be equal to 0, right? Okay, and then scrolling down. You know what, let me clear this first. And okay, I think this is the last one, right? Okay, is that possible or impossible? N equals 3, L equals 2, ML equal -3, and MS is equal to -½
Impossible.
Okay, so why do you say it's impossible?
Because if L equals 2, N can't equal -3.
Okay, very good. Impossible because if L is equal to 2, then ML cannot be equal to -3 because the only possible values of ML in this case would be from +2 to -2, right? And -3 falls outside of that range. Okay, that's it for this chapter, and that's it for this assignment. So what I'm going to do now is create a Dropbox for this assignment. So let me go assignments. So this is assignment number 7. And let's see here. Okay, today is the 31st. So I'm going to let the deadline be November 3rd. Let me go here. And let me do available from today to the 3rd. And save. And And, make sure it's there. Okay, so it's there. So make sure you submit your assignment number 7 by then. All right? Okay, so that's it for today, folks. Enjoy your weekend, and I'll see you next Wednesday.
There's a question about
Uh-huh.
the n equals 9 one.
The what?
The one where you said n equals 9. I think it was the very last question.
Oh, you mean, hold on, let me
Where
see.
you said it had 9 energy levels.
Uh, this one?
Right, yeah. And it said which are possible, but I mean, in the book, right, 2 times n squared is the maximum number of electrons.
Yeah, we're not talking about the maximum number of electrons. What we're talking about is if an electron has these numbers, is it possible?
Oh,
We're not
okay,
talking,
okay.
right, we're not talking
Okay.
about the number of electrons.
Okay, all right, I see it.
So in that case, it would be possible based on the rules that we learned earlier. Good. Okay, and you guys out there in Zoom, I'll be signing off now.